Got an exploration today, so everybody log into Discovery Education. No. Yeah, turn around. All right. So we got an exploration. Let me unfreeze this. I got the reading assigned, so that should be the only assignment you see right here today. Go ahead and click on the reading, and it will take you to this section, which we're going over still evidence for plate tectonics. We're looking for the exploration, so click on Explore More Resources, and then scroll down all the way to the bottom to the exploration, and click on the exploration. So if anybody has problems, if you can't get logged into the exploration, you can't find it, or you get a little behind, let me know. I'll come help you figure it out and get to it before we move on. With the exploration?
Yeah.
So click on the reading. You see the assignment?
Yeah.
Click on that, and then click on up at the top of the page. It should say Explore More Resources. Yeah. And then all the way down to the bottom. Yeah. Nice. Anybody else?
I can't find mine.
All right. Everybody make sure they're following along. If you do all the assignments, you will pass this class. Especially for my seniors that might be close to that cutoff. Second semester, we're doing a lot more of the same stuff. So just you're only in here for 45 minutes. Just follow along. You should be able to complete every assignment. And if you complete every assignment, you'll pass the class. So today we're actually doing something a little bit different. This exploration is going to be a little bit more relating to the actual exploration and not the book. I wish I had brought in my Brunton compass, because I have one from when I went to college. But they're basically going to go over this specific geologist compass, which is called a Brunton compass. It's like a brand name kind of compass. And this is a little bit above and beyond your generic, like, I don't want to get lost in the woods compass. And so they have a couple questions about this, which we will try to answer. But I want to go over the compass itself real quick and look at what they have for the exploration. So one of the big things about this compass is it's not just for telling me what's north, south, east, and west. That should be pretty easy. If you're actually working outside, you should have a pretty good understanding of what's north, south, east, and west. And if you don't, you're going to get lost a lot. This compass is more for telling you about the type of rocks that you're finding. So as a geologist, they're going to send you out into the field, and they're going to ask, what kind of rocks did you see? And what kind of trends were these rocks following? Like, which direction were they headed? Which way were they sloping down? Or which way were they kind of level? There's a lot of different things you can learn. And so one of the things that's different about this, and they have a question about it, which we'll go over in a little bit, the east and the west are flipped. So when you look at the compass, this is the right one. The east is actually on the west side, and the west is actually on the east side. Yeah, it doesn't make a lot of sense when you look at it, but the reason is with a normal compass, and I have one like on my phone here. I just downloaded 2 of them. No, you're right. But I got 2 of them. A normal compass, just the needle points towards the north, right? And what do you want to do when you're trying to figure out which direction you're going to go? You're actually going to turn yourself to where you're facing north. So the actual compass is pointing north and you're facing north. And then you're like, okay, if this direction's north, then that direction's south, this is west, and that's east. But with the Brunton compass, if I switch it over, you can kind of see a little bit. It's got northeast, southwest quadrants. And so the whole idea of a Brunton compass is I would take my compass right up to like a rock shelf or a certain type of rock that I'm looking for, and I actually hold my compass up against it. And so when I do that, instead of telling me which way is north, because I don't really need to know which way is north, this compass is going to tell me which direction my rock is pointing, which is actually kind of important for making maps and understanding what the rocks have gone through. Yeah.
So if it says southwest on the Brunton compass, do you just translate it to southeast?
No, that's why they're flipped. Because look, so on my other compass, let me show you. On my other compass, it's moving around a little bit because we're in a bad reception area. But north is pretty much that way, right? So west is this way and east is that way, right? Now, if I go to my other compass though, and I put it on this little section here, which direction is that kind of headed? If north is this way, it's like a northwest kind of situation, right? So if I do that and they're flipped, when I set this on the side here, you can see it's pointed towards the northwest. That's why they're flipped, because with a Brunton compass, I don't actually move my compass to where it's facing north. I move it to where the rocks go, and the compass should tell me whether it's pointed northwest, southeast, like whichever way we're looking at here. And so it doesn't make sense in your mind, but when you do it physically, it actually tells you the right direction here. Another couple things that they have, it's got a mirror in here with a line in it, and it has several bubble levels. Like if anybody's ever done any construction work and you've used a level that has like the little bubble in the water and you try to make sure that it's nice and flat, it has that here. So you can measure dip, like how steeply inclined a hill or a layer of rock is, and you can measure strike and find out what is actually the flat level. So we'll talk a little bit about those. Let's see what the exploration has and wants from us. So we've got, 10 different points here all across this map. I guess we're going to click on each one and examine them. So it tells us a little bit. I've selected the first location, proceed. So you can see we have different rock layers coming down here. They have the Brunton compass. Let's read with the Brunton compass. It says, identify the strike. So the strike is going to point towards what? This is actually a little bit hard to read. So we have north, south, east, and west. The strike is going to be like northeast a little bit. What is this degree here? The numbers are kind of small. What is this? Is that a 30? 70, 50, 30. Then that would be 10. So this has got to be 20. So I think we're looking at the 20 degrees and not the 200. That's right. Yay, we did it right. Wonderful for us. It'd be nice if the picture was a little bit. Examine another location. Let's see if it does anything different. Proceed. So they asked for another strike. This one's going to be 30, 10. It looks like 20 again. Identify the strike. 20 degrees. Is it going to change as we go? Let's go further down here. Proceed. Read. It all looks like the same stuff. Right between 30 and 10 is 20. Okay, well, I don't want to do this anymore. So let's see if we can answer the questions. And if we need to, we'll come back to this because that's not very fun. Question number 1. What is magnetic declination? Why is it important to set or check the magnetic declination on the compass whenever you go out into the field to map rocks? What can happen if you do not make sure the declination of the compass is set correctly? Yes, why? What is the magnetic declination? Because what is the compass pointing towards?
North.
But specifically, which north?
The
The magnetic north. No, it's pointing towards the magnetic north, where the magnetic north pole is. But when we say north, which is the north we really want to get to? Yeah, which is the rotational north. And so that's what the magnetic declination is. What is magnetic declination? It's the difference between the North Pole and the magnetic North Pole and the rotational North Pole for your particular location. And so depending on what state you're in or what part of the world you're in, it'll be a different number on at different times. So magnetic declination is the difference between the magnetic North Pole and the rotational North Pole. How many degrees difference they are. And why is it important to check or set this whenever you go out into the field? because you don't want all of your measurements to be off. You want to understand exactly what you're pointing at, and you don't want to end up in the wrong place. And that's kind of the same answer to the next one. What can happen if you do not make sure the declination is set? You can end up in the wrong spot or with the wrong measurements, depending on what you're doing. So magnetic declination is the difference between magnetic North Pole and rotational North Pole. It's important to check because you don't want the wrong readings and you don't want to end up in the wrong place. What can happen if you don't do it? You can end up in the wrong place or have the wrong readings. Okay, explain how the strike of a plane is measured. Let me see real quick in the reading if they illustrate strike and dip for us. And if they don't, I can draw it real quick on my own. I don't need them. I don't know that they do. Let me go back to the exploration and see what they say there. Explore. I don't know that they do. So let me see if I can draw this real quick. I don't think it'll take too long. I don't want to draw it way over here. I need a third board. So what do we have here? We have, am I going to do a hill or a mountain? I'll do like a mountain hill. We have a mountain hill here. I've got I'm like right here. That's me. Woo! And they want me to get to the other side of the mountain, right? There's two ways that I can go about this. There's a lot of different ways to get to the other side of the mountain. But what's the number one way to get across to the other side of the mountain? Yeah, go over. You're going to go all the way to the top, go over, and then come down the other side to the bottom, which is cool. You'll get the best views. You'll get to put your name on the list of people that actually got to the top of the mountain. But going up a mountain is a lot of work. The other thing I can do is I can just come around the side of the mountain. It's almost three-dimensional. I'm not very good at drawing three-dimensional things. But I can just walk around the side of the mountain, never going up or down, but just kind of stay at the same elevation and get over to the other side without climbing up or down.
What if it's a weird mountain and it's flat on the sides and you're going there?
Yeah, then you can't walk around the sides. But for most hills and mountains, you will be able to take this path. Now, what this means is you're walking along the strike. And I wish I had a better way to kind of illustrate this. Let me see. Can I draw very well at all? I don't know. Maybe. I don't know my perspective's right here, but no, that's not good.
Yeah, that's pretty good.
No, it's not. It's not going to work for me. It's not what I want. Let me grab one of these books real quick just to show y'all. So, the strike, if I have like an inclined plane, the strike is going to be the part that's horizontal, that's perfectly flat. So if I walk along this line, I won't walk uphill or downhill at all. I will always stay the same elevation, and I won't spend very much energy. I have to walk further, but I'm not going to go up or downhill. That is the strike. It's perfectly level. The dip is going to be what goes directly downhill. The steepest downhill part is the direction of the dip. So when they talk about strike and dip, that's what they mean. Strike is the direction where you're perfectly level and you're not going uphill or downhill. Dip is the level or the measurement where you're going the most downhill. It's the most inclined part that you have. So explain how the strike of a plane is measured. You're going to take your Brunton compass. Actually, let me see if I can do this. So your Brunton compass, if we go back to it, has these levels on them, right? I'm going to take my Brunton compass. I'm going to put it up against my rock that's inclined, and I'm actually going to take it and move it until that level is nice and level. This one in particular, actually you could use either one of these depending on how it's set up. But I'm going to move it until my level reads nice and level. I know that is flat. And now my compass is pointing towards the direction that is going to be my flat direction. So like right now, it's saying it's like southwest is my flat direction. So if I just walk at that direction southwest, I'll never go uphill or downhill. I will just walk nice and even, and I'll have a nice easy path to kind of travel along. So for the Brunton compass specifically, how do I explain how the strike of a plane is measured? You're going to orient your compass or turn your compass until the level tells you that it's flat, that it's nice and flat, and that is the direction of your strike. That is the strike of your plane. So explain how the strike of a plane is measured. Take your compass up against the rock itself, and you're going to move your compass until it gets until the level says that it's flat. Once the level says that it's flat, that direction is the direction that your strike is. It's your even, like flat, horizontal direction. Yes.
Why can't you just walk?
Huh?
Why can't you just walk? Why do you have to be
Oh, you can. Well, this isn't for like leisurely hiking.
Do people actually do this?
Yeah. I had to go. So to get my geology degree, I had to go out into the field for like a month and do this kind of stuff.
You use the Brunton compass?
Oh yeah. They have more technologically advanced ones now, but a lot of times when you're looking for oil and gas formations, you're in an area that doesn't have good like cell phone coverage. So unless you have like an expensive actual GPS that connects to satellites, it's difficult to make all these readings digitally now. But yes, this is important because where stuff comes out at the surface is going to tell you about what they're doing underneath the surface. So, for example, if I'm looking like for some oil and gas, and I'm walking along the surface here I am. It's a bad picture, but I'm walking along the surface, and I find all these rock layers that are doing this number here, but on the other side, they're doing this number here. That tells me that I have this big anticline system, which I don't know that we've gone over those, but I have this big system here, and if it keeps going like this, I could have another one down here where I have a bunch of oil and gas track. Should be somewhere that I want to drill. And so that's like, it doesn't seem like anybody does this. People do this all day, every day, especially in Texas. You need to know what's underground to know where to drill. Drilling oil wells is super expensive nowadays. You're talking, I think, minimum $15 to $30 million per well. A lot of them are a lot more expensive than that. And so as a geologist, if I don't do this work and I'm like, yeah, drill a hole here, and there's no oil or gas that comes out, like I've literally just cost the company more money than I'll make in my entire lifetime. They're gonna fire me. So yeah, you gotta know what's going on at the ground to know what's going on underneath the ground, and it's actually pretty important. So number 3, the directions east and west appear reversed on the Brunton compass. Explain. They are reversed on the Brunton compass. The east and west are reversed, and the reason is because the Brunton compass isn't designed to tell me what direction I'm facing. It's designed to tell me what direction the rock is facing. So I don't reorient the compass to match north, and then it tells me what's east and west. I'm reorient the compass to match the rock, and it tells me which direction the rock is going. And so for that to happen, it's got to be reversed from the normal east and west. East has to be the west direction, and west has to be the east direction. So explain. This is because, I don't know. Yeah, it's not telling me the direction I'm facing. Is that the right way to put it? It's telling me the direction the rock is facing. I guess that's good enough. Number 4. What is the difference between azimuthal notation and quadrant notation while using a Brunton compass? Provide 4 conversions of azimuthal and quadrant notation. So here we go. Azimuthal is going to be a full 360 degrees. So if I spin around all the way from north, all the way through all the directions back to north, I've gone 360 degrees, right? That's azimuthal. So it goes from 0 to 360. Quadrant notation is the one where they separate it into like the north, south, east, west quadrants. So azimuthal is from 0, you go all the way around to 360. With the quadrants, I have it broken up into north, east, southeast, southwest, northwest, and I will only have 90-degree variance there. So I have from 0 degrees to 90 degrees northeast, 0 degrees to 90 degrees southeast, 0 degrees to 90 degrees southwest, and 0 to 90 northwest. So that's the difference between azimuthal and quadrant. Azimuthal is the full 360. The quadrant is separated into those 4 quadrants: northeast, southeast, northwest, southwest, and they're each 90 degrees. And you don't have to provide the 4 conversions. It's fine. Number 5. In this exploration, the Brunton compass is used to measure the strike and dip of an outcrop at a given location. Describe some other uses of the Brunton compass. They have the strike, the dip. What are other uses of the compass? Strike, dip. That's mostly it. Direction. Let's see. Do they tell us? Apparatus, compact. I wish you could read the words better on here. Strike and dip of fault planes, layers, and rocks. Magnetic compass needle. Bullseye level. All right, so it can measure the angle of the dip. Let's see. Strike and dip of an outcrop. Yeah. I don't know. What else can it use to be measured? I put direction there because they didn't list direction in the actual description. Angle of dip. Angle of dip. So the dip itself tells you which direction is the furthest downhill. So like if the direction is north, if I walk north, I'm going to be going downhill at the steepest part. But it doesn't tell you how steep it is. It could just be a little bit downhill or a lot downhill. The angle of dip is something else that you can measure. And I guess that's the only 2. It's got a mirror on it, so you can do some weird stuff with the mirror. They told us if we needed to, we could start a fire with the mirror, but I don't think that's true. Geology teachers, trying to get you to buy a fancy, expensive compass. And they're like, look at all these things you can do with it. It's just a regular mirror. It's not like a magnifying glass or anything. But yeah, I'll just put direction and angle of dip. Direction and angle of dip for number 5.
We should try it.
Number 6. If I had thought about it, I would have brought mine up here. Maybe I'll bring it tomorrow.
Wait, direction of what?
Direction and angle of dip. Direction's one thing. Angle of dip is a different thing. Describe the typical deformation associated with the following tectonic boundaries: convergent and divergent. Okay, so let me actually get this real quick. This will help out.
I want to go in there.
Okay, we haven't fully gotten into this yet with structure, I don't think. We didn't do anything with these yet, did we? All right. So first off, we have two words here. Convergent and divergent. What's the difference between convergent and divergent?
Convergent, convergence, divergence.
Yes, but don't use words to define themselves. Convergent, coming together, divergent, splitting apart. There you go. So convergence, coming together, divergent, splitting apart. If I take rock layers, use your imagination, these are rock layers, and I squeeze them together, what's going to happen to these rock layers?
Sedimentary rock.
No, what's going to happen to them? If I squeeze them together, what's going to happen?
Yeah.
These are going to fold. So look, what is one thing that I can have with convergent boundaries? I can have folding. Folding is a part of things that happen in rock, and we will see that happen. That's actually kind of what I have going on over here in this little drawing that I drew. These are folded layers. And so that fold can help us understand about the history of the geology. Another thing that happens, if things don't bend, what do when you try to change how they're shaped? They break. So instead of folding, if I squeeze this together, what's going to happen to the rocks? They're going to break, and I'm going to get a fault. So squeezing together, this is a specific type of fault, which we haven't gone over yet, but you can put it down in the answer. This is going to be a reverse fault. So, but folding for convergent, folding, and reverse faults. Huh? Yeah, that's the grass in the river. Yeah. The other thing you can do, so instead of convergent, squeezing together, what's divergent? Pulling apart. Now, if I pull these apart, what's going to happen? This is going to drop down, right? When I pull them apart, I'm going to have a sliding the other way. So this is called a normal fault. So divergent is going to be normal faulting. Divergent is normal faulting. Convergent can be folding or reverse faulting. And I think that's it. Those are your major types of deformation. So, noise. Number 7, determine whether the following statements are correct. If incorrect, modify the statement such that it is correct. A, in a convergent tectonic environment, plates move towards each other. Does that make sense? Convergent towards each other? Yeah, convergent, things converge, they go towards each other. And collide to cause deformation. Does that sound okay? Yeah.
Like if let's say it's true, can we just put A true, and then let's say B is not true, can we just put B and then write it true? Like,
Yes, yeah. So that's what we're going to do. But is A true? Yeah, A is true. In convergent, they move towards each other, and eventually they'll smash into each other and cause deformation, just like a car wreck. B, in transform tectonic activities, plates move away from each other to cause deformation. Again, we haven't really done this yet, but in transform, what actually happens, instead of pushing together or pulling apart, transform, they go side by side. And so it's not going to move apart, move away from each other and cause deformation. It's really just going to slide horizontal to each other. And whether there's deformation or not really depends on the fault. So I would just say that B is not true. To write it true, I would say in a transformed tectonic environment, plates slide horizontally next to each other. I guess I'm not great with English sometimes. Plates slide horizontally with respect to each other. So in a transformed tectonic environment, plates slide horizontally next to each other. C, in a monocline, layers dip in the same direction. What does mono mean? One. So if I have a cline or an incline that is described only as one, everything's going to be in the same direction, right? Like this wouldn't be a monocline because I have stuff going in different directions, or even if I made it like an upwards and a downward bend. But a monocline is just like basically a one-sided hill. So that is actually true. In a monocline, layers dip in the same direction. All the layers dip in that same direction. And then D, the dip of a vertical feature is 0. Does that make sense? Or what should it be instead of 0? Someone said it. Yeah, 90, yeah. Because 0, if I have 0 dip, that's just flat. But if I have all the dip, 90 degrees, that's going to be vertical. And so that's how you would change that to be true. The dip of a vertical feature is 0. Although I guess technically you could say the dip of a horizontal feature is 0, and the dip of a vertical feature is 90.
Then you just
But
change it
either
to
way.
horizontal.
You can change it to horizontal, or you can change the number to 90. Both of those technically would be true. So you got to think about it both ways. Both ways. Gotta open your mind, expand your horizons. Number 8. In this exploration, you collected data not only the strike and dip of the rock layers, but also the rock type, fossils present, and ages of the layer. We would have done that if we would have finished it. Explain how each of these pieces of data helps the geologist interpret what the formation looks like underground and what the formation can tell us about the tectonic history of the area. So let's go step by step through this. They say we measured the strike and dip. The rock type itself, what kind of rock is it? Is it igneous, sedimentary, metamorphic? What specific type of rock? The fossils that are there and the age of the layers. Explain how each of these pieces of data helps the geologist interpret what the formation looks like underground and what the formation can tell us about the tectonic history of the area. So let's just go through this. The age of the layers can tell us how old something is and kind of what was going on when it was born, right? Like for each of y'all are all born around the same time, but some other random person that doesn't know anything about you, if they came up and met you at a party or something and knew your age, they'd probably know kind of like what kind of cartoons you watched when you were a kid, because everybody that's the same age watched the same kind of cartoons. They would know like what sports teams were winning when you were in high school, as opposed to the sports teams that were winning when I was in high school. Just by knowing someone's age, you can know a lot about the history of their life without actually having met that person and know their actual history. So age of the layers tells us how not only how old the rocks are, but what was going on in the time frame that they were kind of created, and since they've been alive. The fossils tell us where those rocks have been. If I have fish fossils, was this rock like up on a mountaintop or anything? No. If there's fish fossils, it was underwater. It was either under the ocean or under a lake. If I have like tiger fossils, it wasn't in a desert. It was in a forest somewhere. And so that's the kind of things that's telling us there. So fossils will tell us what the rock, what kind of areas the rocks have been in. And the strike and dip of the rock layers will tell us, like I said, what kind of trends we can expect to see underground. So if they're at a certain angle at the surface, they're probably going to continue that angle underneath the surface, and we can kind of build a picture of what the rocks would look like underground. So I know that's a lot to type, but that's kind of what they're looking for here. So age of the layers are going to tell us about what type of environment they were born in and kind of what they've done since that happened throughout their life. The fossils will tell us where the rocks have been and what kind of environment they've been in. And then the strike and the dip of the rock layers will tell us what direction they're headed underground and what we might expect them to do underground.
Are we doing all 11?
No, we're going to stop at 10. We won't do that second page. So when you get done with these 10, submit, and don't worry about that last question, number 11. Number 9, assume that the structure you explored in this exploration is real. Explain how it formed in terms of the theory of plate tectonics. Let's just go and see real quick what we can do here. Because they're not showing us. I don't even have anything collected over here, so I guess maybe I didn't finish it. What am I supposed to do here? Put this, examine, proceed, read. It was 20. Record. That's right. I know it is. Proceed. There's more stuff to do. Identify the dip. The dip will be right here. It's like 90 something degrees. What? No. Hold on. Oh, because they have it in the southeast. So, yeah. This is north, south, east, west. So this would be southeast. Yeah, 5 southeast. Good job. Record. That's right. And, okay, so I guess those are the two. Yeah. But is that actually going to tell us about anything? I don't know about this. Might just skip number 9.
Sounds good to me.
20 degrees, south 20 west or north 20 west. This is going to be the north 20 west. Oh, never mind. Identify the dip. 25 southeast. Nice. Yeah, I don't know that it's really painting a picture here for us or anything. So let's just skip that one. I don't mind. Skip number 9. I'll allow it. Number 10, describe how the measurements you made would differ from if the information was an anticline, a monocline, or undeformed. I guess skip number 10 too, because that's related to number 9. So that's it. 1 through 8. Do number 1 through 8. Submit, and it should be good. Does anybody have questions about any of them? Want me to repeat any of them? Number 4. Hold on a second. I'll get to you next. Number 4. What is the difference between azimuthal notation and quadrant notation? Azimuthal is all the way around in one group, 0 to 360 degrees. The quadrant notation has it split up into northeast, northwest, southeast, southwest, and they're 90 degrees. What did you need, Brandon?
Number 2.
Number 2. Explain how strike of a plane is measured. All right, so for that one, it's weird. I don't know how to say it. So to measure the strike of a plane, I've got like an inclined thing here. What I'm going to do is I'm going to take my compass and like orient the compass where the level says that it's flat. And so once the level says that it's flat, that direction that it's pointing is the strike. So if I walk that direction, I won't go uphill or downhill. I just say at the same, elevation, Which I don't know. That's weird to type in a sentence, but there it is. All right. Anybody else have any more questions they want to fill in? 1 through 8. At least get something in there to submit so I can give you a grade for it. If you have any questions, let me know. Email me, let me know after class, come in during activity period, or hop on Google Classroom and watch this video because I go through everything on the video. So, cool.